Welcome everybody to our session today with DOE Zero Energy Ready Homes Technical Training Series. We're excited that you can join us today for today's session on efficient hot water distribution in Zero Energy Ready multifamily buildings. Today's main presenter will be Gabe Ayala of Enovative Group Incorporated. And today's session is just one in a continuing series of training webinars to help support our partners in designing and building and selling Zero Energy Ready homes. My name is Jamie Lyons, and I serve as the Technical Director for the Zero Energy Ready Homes program. And before we dive in, let me just hit a couple of housekeeping notes here. The first of which is that we are recording today's webinar, and that makes it possible for us to then post it on the DOE Zero Energy Ready Home website, where it will become one of 24 or more recorded tech training webinars in our library there. So we invite you to go there and take a look at all the other offerings. The second item is that the attendees in today's webinar will be on the listen-only mode. And if you do have questions, we invite you to type them into the questions pane, and we'll monitor these throughout the webinar, and we'll pick up questions as we go through the webinar, and then we'll have a little bit of time at the end. We are planning on a 60-minute webinar today. So before handing it over to Gabe, as we do these tech training webinars, I'd like to offer a little bit of context to why we're looking at a particular topic. So as you see here on the screen, these are mandatory requirements for projects that want to be part of the DOE Zero Energy Ready Home program. And you can see that fourth item there is water efficiency, and it calls for the hot water delivery systems, whether they be a distributed system or a central system, to meet energy efficient design requirements. Gabe will get a little more into what are some of the energy implications of how we design and use hot water distribution in multifamily. Second item to point out on the slide is that we're referencing the Rev 6 specs for the program. That means revision 6. And these were just recently released. They're posted on the website now. In a nutshell, they mostly contain clarifications, but there are a couple important changes made. And notably on this slide, we see that the building eligibility has been broadened a little bit with the release of the Rev 6 specs for the program. And we list out the eligible building types here. And those that you see in the bold font indicate there's a sort of a broader footprint of multifamily buildings that can be part of the program now. We can have multifamily buildings 3 stories or lower, also 4 or 5 stories above grade, as long as 80% of their square footage is residential in nature. And then this last sentence down there above the 3 pictures, it's also important. It indicates that eligible multifamily buildings can have central heating, they can have central cooling, and or central hot water systems. And if we're in that territory, there's no longer any requirement to have a solar hot water component as part of a central hot water system. And I just mentioned that because in prior versions of our program that provision did exist. That's no longer the case. The other thing to note about these eligibility provisions is they are directly in step with Energy Star Homes that also updated its eligibility provisions in the exact same manner a couple months ago. So we're in lockstep with Energy Star Homes as far as what types of multifamily buildings can be part of the program. So, and then a quick word about central hot water systems. If we're in a multifamily setting and a project is using central hot water delivery, then the Zero Energy Ready Home program does require a few provisions on that type of a system. We're looking for that system to be used on-demand recirculation, so it's not just running 24/7, which incurs significant energy penalties. To do that, we look for that system to have 2 signals governing its operation. The first is there's a demand indicator. So we don't need to circulate water through a hot water circulation loop unless we have some indication of demand. Somebody in the building wants to use hot water. And secondly, we want to monitor the loop water temperature, so we know that we need hot water to be circulated through the loop. If the loop water is already hot enough, then we don't need to recirculate water. So those are the two indicators that should operate the on-demand recirc. And then as far as what the field verification entails, it's pretty basic right now. We just want to make sure we're getting the basic things right. Pump is pointed the right way, the temperature sensors are installed and ready to help control the system's operation. And then down here at the bottom, there's 3 advisories. These are sort of good practices that DOE currently encourages, but they're not requirements at this time. The first deals with stored volume between the recirc loop and the furthest fixture. It's recommended that that be 1 gallon or less. Pipe insulation, recommended at R4 pipe insulation, or whatever the local code may dictate. Local code would always prevail, of course. And then finally, the recirculation pump, it's watching that loop temperature, and it's encouraged that the loop pump operate if there's at least a 5-degree difference between the loop temperature and the water heater set point. So those 3 items are advisories at this point. As more and more of our stakeholders get up to speed with efficient central systems and multifamily, these are good things to incorporate into your designs. So today's webinar, sort of sneak preview of where Gabe is going to go. A little bit of background about hot water energy use in multifamily buildings. And then he's got some really nice content on these 5 design elements of central hot water systems in multifamily. And I highlight that second bullet because that's where the Zero Ready spec requires those provisions that we just looked at. But he'll go beyond that into some good practices for other elements of hot water distribution design, as you see there. So with that, I'm going to run a quick poll just to learn a little bit more about who's on the session today. And while I run that, I'll introduce Gabe and then hand over the presenter reins to him. So you should see a poll popping up on your screen. The standard poll, just trying to get a little more insight on who's attending today's webinar, and Gabe may tailor some of his remarks accordingly. I'll give everybody another second to respond, and then we'll show you the results. All right. So while you guys take a quick look at the results, you can see we're majority energy consultants with significant groups of engineers, architects, and the all-encompassing other category. Turning it over to Gabe Ayala. Gabe is a co-founder and chief business development officer for Enovative Group, Inc., where he oversees R&D as well as strategic growth initiatives for the company. He has been in hot water for over a decade, having led CEC-funded research and developing products to help improve hot water delivery in buildings both small and big. Gabe, you all set?
I'm all set.
Take it away.
All right. Thank you, Jamie. Good morning or afternoon, wherever you are, and thank you for joining us today. My name is Gabriel Ayala with Enovative Group, and the title of today's webinar is Efficient Hot Water Distribution in Zero Energy Ready Multifamily Buildings. So, as Jamie mentioned, I'm going to go over some of the elements that I believe make up an efficient hot water distribution system for multifamily central hot water. But first, I need to figure out how to get control of the screen. Let's see.
I just sent you an invite to make you the presenter. You should see that pop up here.
Okay. Is it coming in through my email?
Come up right through the webinar dashboard. You should see an invitation to share your screen. If not, we can revert to me forwarding the slides, whatever would work better.
Let's see here. Sharing. Yeah, I'm not seeing it.
Want me to continue with the slides, Gabe?
Yeah, sure.
Okay.
Now, Jamie, I have to tell you, I can't see. Oh, here we go. Now I see it.
There we go. Sorry, everybody. We'll continue. See your first slide now?
Okay, yep. So, as I said, we're going to be talking about efficient hot water distribution, and we're going to keep this limited to multifamily buildings that are low to mid-rise, so about 1 to 5 stories. Anything that's above 5 stories we would deem a high-rise building, and it's a little bit different beast. So, but hot water, I believe, is an important and relevant topic, as hot water energy use constitutes almost 20% of total energy consumption in residential buildings in the U.S. And what you'll learn today is that there's more to efficient water heating than just the efficiency rating of your water heater. So, the topic of hot water distribution actually has nothing to do with the manner in which water is heated. It only deals with how hot water, once heated, gets to the user through the network of piping, whether that be efficiently or non-efficiently. So we're not going to be talking about types of water heating or methods for water heating. So, yeah. Can you go to the next slide? First, a real brief introduction to who Enovative is. We are a Los Angeles-based company. We are a manufacturer of demand recirculation systems for both residential and commercial buildings. We conduct independent and government-funded research, mainly in the field of hot water and hot water distribution. That's been sort of our core competency. And then we also provide retrofit services for residential commercial buildings and implement utility efficiency programs. So we're, trying to help upgrade the existing building stock as well as improve performance in new construction. Next slide. So in a central hot water system, it's important to make a distinction that in apartment buildings you have 2 types of hot water system architectures. You have what Jamie referred to as a distributed hot water system, where each individual unit has its own water heater and distribution piping. And then you have the central systems that serve multiple dwelling units. So for the purpose of this discussion, we're just going to be talking about central hot water systems, as they are more prevalent in buildings, and it's probably mostly due to lower upfront costs. So a central hot water system is made up of a water heater or boiler, or it could be a bank of heaters or a bank of tankless water heaters. Typically, though, there is storage, hot water storage. They have a recirculation pump and piping that circulates hot water from the boiler room through the building and then returns the unused hot water back to the boiler room. So next slide. So this is a chart I often show in presentations, I think, as it speaks to just how inefficient central hot water systems are. So what you're looking at is a graph depicting the energy flow in multifamily central hot water systems in the state of California. About a decade ago, the California Energy Commission began focusing research efforts on multifamily central hot water. In about 2011 is when the statewide codes and standards team published findings on field research throughout the state. And according to their analysis, only about 1/3 of the energy that's put into these central systems comes out as hot water at the tap, and the rest of that energy is just lost. So you have approximately 1/3 of it is lost in the water heating room through combustion losses and standby losses, and then you have approximately another 1/3 that's lost in the recirculation loop. So, this represents one of the most energy wasteful subsystems in the building. And although this research took place in buildings throughout California, California does have 16 different climate zones. a wide variety of building types and vintages. So I think that makes it a relatively fair representative sample of buildings throughout the U.S. So, you know, the problems that buildings are facing in California, I think we can safely say we're seeing in other parts of the country as well. So, but if you want to click the next slide, what we're going to be focusing on is the recirculation loop and the distribution of the system that, as I said, has roughly 1/3 of all the energy loss. Okay, next slide. So now that I've warmed you up to the basics of this topic, I'm going to cover these aspects of distribution and sort of go over what are the best practices for wringing the waste out of the buildings. So these topics are, in no particular order, pipe insulation. So what pipes need it? What are the best R levels? Recirculation controls, what are demand controls, how much energy can be saved as a result, system balancing, what are the best balancing options that are available, and how does domestic hot water balancing differ from, say, hydronic balancing, and then crossover prevention. What is crossover? How does it affect energy performance? What are methods for prevention? And then finally, we'll go over optimized loop design. How should the pipes be run? And what else should be considered when designing the recirculation loop. Next slide. So the first thing is pipe insulation. One of the easiest and most cost-effective ways of mitigating heat loss in central hot water distribution is by adding pipe insulation onto the hot water pipes. So this might seem like an obvious and intuitive measure, and you'd be absolutely right, it is. But you would be surprised also by how little pipe insulation is actually used on the entire loop. It wasn't until the most recent energy code versions of Title 24 and IECC that made hot water recirculation loop insulation mandatory. So if you think about most of the existing buildings that are out there have no insulation once they leave the boiler room. And sure, you could have pipe insulation, you know, on the pipes that are within the confines of the boiler room, but really once they leave, they're mostly uninsulated. So pipe insulation comes in a variety of materials and R values. You have, you know, the thermoflex that you see here. You could have insulation that's made out of fiberglass that has a relatively better R value. But really anything that you use is better than nothing. So, and you know, if there's anything that you remember from this presentation is that pipe insulation should be automatic, just because, you know, there's no going back to insulate after the building has been built, unless you're planning some major repipe. Usually, you know, once that building is built, then, you know, you're not going to be able to go back to add insulation in a cost-effective manner anyway. Next slide. So the recirculation loop is the area of most concern as far as insulation because it has the most surface area. Heat loss in piping is a function of the surface area of the pipe. So it's recommended that you use a minimum R4 insulation to insulate the entire recirculation loop. For Title 24 and IECC, in addition to the recirculation loop, all additional piping that's a minimum 3/4 inch must be insulated to a minimum R4 value. But in reality, it's recommended that all hot water piping should be insulated. Next slide. So what impact does insulation have on heat loss? Well, as you can see from this graph, basically R4 insulation triples the cool down time of 3/4 inch pipe. So if you look at the graph, you have this is the time it takes for hot water to cool down to 105 degrees. So if you have 135 degree water in your 3/4 inch pipe with no insulation, it takes a little over 20 minutes to cool down to 105 degrees. Whereas if you have a minimum insulation, it'll take over an hour to cool down. So that just illustrates how important pipe insulation is on reducing heat losses. Okay, next slide. So the second chapter of this presentation is looking at recirculation pump controls, which is another major area of energy loss. And actually, this is an often overlooked area for energy efficiency savings, as the benefits of recirculating pump controls on these types of pumps are generally misunderstood. Because first of all, these are, we're talking about small fractional horsepower pumps, right? Not a lot of electricity to operate these pumps. So when people are thinking about pump controls, they think about the electricity savings, but really what we're talking about here is regulating the runtime of the pump to reduce the thermal losses in the pipes. So let's discuss the function of the recirculation pump. The job of this pump is to bring the source of hot water closer to the points of use in order to reduce wait times and water waste. The problem is that most of these pumps are just left running on a continuous basis 24/7, regardless of whether or not hot water is even being used, and regardless if there's sufficient hot water through the pipes already. So running these pumps continuously, not only is it unnecessary, but what happens is it requires the water heater to constantly fire up to make up for line losses. So the strategy is to turn the pump off when it doesn't need to run. You offset some of those losses and the water heater becomes more efficient. So domestic hot water recirculation pumps differ from pumps used in other applications such as chilled water loops or condenser water loops, hydronic systems. In those cases, the pipes that have fluid circulating through it are closed loops, meaning that water's never leaving the system. But in a domestic system, you have dynamic flows where people are using hot water, water's leaving the system. So those draw flows that occur as a result contribute to those heat losses. Next slide. Part of an efficient recirculation loop is having proper configuration of the loop. Not just in terms of maintaining the function of the system, but for also maintenance as well. So here we see a diagram of what I deem is a proper recirculation configuration, and it's a very basic version. Obviously, in large buildings, it might get a little more complex than this, but for to keep things simple, I'm going to just keep it very basic. So you have cold water coming in from the city, goes into a boiler where it's heated, and then it's transferred to a storage tank. And then from the storage tank, hot water goes out to the units. And then at the end of the building, there's return piping that brings that unused hot water back, and it just circulates. Now, what I want you to pay particular attention to, however, is the return line back by where the pump is, because this is an area that's very crucial in order to maintain proper operation. So you have the pump that's on the return line, and then you have two isolation valves so that you can easily service the pump, and then you have a hose bib for purging air out of the line. So one of the main reasons for recirculation pumps to fail is because you get air caught in the return line, and there's no way for that air to get purged out. And so that typically will burn the pump out, and it doesn't circulate hot water, and then obviously tenants will complain that they're not getting any hot water. And then downstream of that hose bib is a check valve, and so you want to make sure that that check valve is there to prevent both backflow, which will cause crossover, as well as when you're purging the air out of the line, you want to make sure that when the hose bib is open, that water is coming through the return line and not coming through the cold water main coming into the building. Okay, so next slide. So demand controls are an advanced recirculating pump controls that regulate the runtime of the pumps to only the times when it's needed. and it results in a reduction in recirculation loop heat loss. This, in effect, results in the boiler or water heater having to cycle on less frequently, thus resulting in a drop in natural gas use. In addition to saving energy, however, pump controls will aid in the reduction of pipe erosion and pinhole leaks. So there's both energy and non-energy related benefits for this measure. Next slide. So in a demand control, as Jamie pointed out earlier, it uses two sensors that work in concert with one another to regulate the runtime of the pump. First, you have a flow sensor that is put into the cold water makeup or the cold water inlet to the system. It can also be put on the hot water supply going out. But what this flow sensor is doing is it's registering when there is a draw flow, when there's hot water demand. So it's important that the flow sensor be put on an area of the piping that's able to effectively read draw flows in the building. Whenever there's a draw flow, then it's going to check the return line temperature to see if it needs to turn on. So if there is already sufficiently hot water in the building, the pump does not need to activate. But if it sees that it's dropped below its target temperature, then the pump turns on and it just runs for as long as it takes for the return line to get back up to its target temperature, and then it shuts off. So operating in this fashion will reduce the runtime of the pump from 24 hours a day to roughly usually about 3 hours or less per day total, while still preserving the same level of hot water service to the occupants. In my experience, the buildings that are on the smaller side of things, like 5 to 20 unit apartment buildings, we generally see a runtime of less than 1 hour per day. So the pump runtime, or the pump on time, is usually off 90% of the time. So demand controls can be designed into the plumbing during new construction, and it also can be installed into existing buildings as a retrofit. And in fact, there's many gas utilities in North America that right now that provide pretty good rebates and incentives to retrofit existing buildings pumps with demand controls. In California, the Southern California Gas Company has a program that installs them at 100% no cost. So there's a lot of buildings in California that have been retrofitted with demand controls. Next slide, please. One of the important installation requirements for demand controls is where to put the temperature sensor on the return pipe. This can be crucial because even though it's a fairly simple control system, there is some nuance to the installation, and if it's not done just right, then you could have areas of the building that aren't getting hot enough water or sufficiently hot water, and then obviously then you get tenant complaints. Whenever there's a tenant complaint, rest assured controls are bypassed and deactivated. So that's not what we want to happen. In this example here, you see two return lines coming back. Presumably these return lines are servicing different zones of the building. And so these two return pipes are coming back, they're joining to make one common return pipe, and then that's where the recirculation pump is. Now, if you were to put that temperature sensor just upstream of the pump after those two pipes join, well, one circuit is going to be a shorter path than the second. And so when that gets hot, that's going to tell the pump to turn off. But if the second leg or the longer loop hasn't had enough pumping to sufficiently get hot water through, then the pump's going to turn off prematurely. So what you want to determine is which return line is longer, which one takes longest to get hot, and then that's where you want to place that temperature sensor. Okay, so next graph, or next slide. So this is a graph to give you an illustration of how pump controls affect the water heating gas use. So this was taken from a data logger that was put on the gas valve of a water heater. And it's over the course of a 1 week period of time. The first half of the week, the pump was running on demand control. And then the second half of the week, the control was bypassed and the pump just ran on a constant basis. And as you can see that when the pump is running continuously, the water heater is having to fire up far more frequently to make up for the losses from all that hot water getting pumped out into the building. So this just helps to illustrate, the impact that pump operation has on water heating operation. And on the next slide here, I have another illustration that I think is really telling as well. This was taken from a student dormitory last summer in University of California, Riverside. And in this building, it was during the summer months, so it was unoccupied, or there was very few occupants, so there was very little hot water demand. And what you can see is that, what we did is we were tracking the runtime of the water heater, and we switched the mode of the pump operation from continuous to demand every other week. So every other week we were switching it back and forth, and just reading the gas valve runtime. And what we were seeing is nearly a 50% decrease in water heating gas use just by controlling the recirculation pump. That's how much of an impact on some of these buildings, these little circulation pumps, how much effect it has on the energy performance. Next slide. So as Jamie mentioned before, the demand controls are a new requirement to meet the Zero Energy Ready Homes program. And it is also the new requirement for California Title 24 for new construction, as well as the 2015 IECC. I believe now there are about a dozen states that have formally adopted the 2015 IECC building codes, which demonstrates that these state governments are taking it upon themselves to lead the rest of the country in building energy performance. Next slide, please. So the next chapter here is on crossover prevention, and this is a topic that's near and dear to my heart, because we just finished up a 3-year study for the state of California on this subject. Crossover is the uncontrolled mixing of hot and cold water in a plumbing system, usually due to a faulty or failed mixing valve or mixing valve cartridge, for like a shower. But it can also occur anywhere in the building where hot and cold water pipes meet. So I guess the best way to explain crossover is, have you ever taken a shower in an older hotel or apartment and get sudden spikes of hot or cold water, or you're just not able to get a stable, consistent hot water temperature? That is probably the best example of what crossover is. So here we see a photo of the back of a shower mixing valve, where the hot and the cold water pipes meet into the valve on the left and the right. The pipe that's going to the top is going to the shower head, and then the pipe going down is going to the tub spout. And so this is where we most commonly see crossover failures occurring. And crossover has an impact on the energy performance of the system. Next slide. So here's a good way to show what happens during a crossover event. So without crossover, a properly functioning mixing valve will keep the hot water on the hot side and the cold water on the cold side, and then allow the user to mix any portion of the two to get the desired temperature out of the faucet or out of the shower. But when these little stem cartridges in the mixing valve, when they start to go bad, it creates an open circuit that allows the water to move freely into other side. So when there's a pressure drop on one side, water will unintentionally cross over into the other. So if you have your hot water circulation loop going right, and there's a high amount of hot water demand, that could cause the cold water to get in and diminish the embedded energy value of the hot water circulation system. So this is a problem that, as we learned in our research, is fairly common. We performed a crossover test in over 100 buildings throughout California. And what we found was that in about 52% of buildings had some degree of crossover issues. But One interesting thing about this problem is that sometimes the problem is very noticeable, like when you're feeling the fluctuation of hot water. Sometimes the effects are that you can't ever get hot water. Maybe you can get hot water out of your kitchen faucet, but you can't get hot water out of your bathroom faucet. But other times it is completely asymptomatic, meaning that it just goes unnoticed, and people will get a usable temperature, but the energy losses are still persisting over a period of time. So in our research, we realized an average savings of about 16% of total hot water energy use just by repairing the valves and completely eliminating the crossover. Next slide.
Gabe, could you repeat that last stat? What were the energy savings from eliminating the crossover?
So we took 10 buildings that had not known crossover, and we measured the baseline conditions, and just by repairing the crossover and eliminating the crossover, we realized an average of about 16% of total hot water energy use. So I would say fairly significant.
Yeah, thank you.
Next slide, please. So our research concluded by making the following recommendations to codes and standards for crossover prevention. Number one, to only use ASSE 1016 approved shower valves or fixture valves. And ASSE is a plumbing standard. And what these valves provide is for a pressure balance, meaning that if there's a pressure imbalance on either side, it's going to self-regulate it to help reduce the crossover effect. However, we even found some of those valves in the field over time have failed as well. Water, especially hot water, is over time can damage just about anything. And so in addition to that, we're recommending that all of these valves have integral check stops. In addition, we also want to make sure that there are check valves that are going into the cold and the hot water lines into each individual apartment unit. And then finally, we want to make it easily accessible to change out those fixtures when they need to be changed out. So, have easy access panels to the shower valves in order to replace it, and also have isolation valves so that you can work on it. There's nothing more frustrating than when you have to post a hot water shutoff notice to an entire stack of units because you need to go replace one shower valve cartridge, and then also, it's frustrating if you have to knock out a bunch of tile to repair or replace a shower valve. So that makes those replacement projects all that much more cost prohibitive. Next slide. So here's a simple graphic to help illustrate where the isolation and check valves would go on each individual unit. So when the hot and cold water lines, when they branch out into the unit, that's where you want to have your check valves to prevent backflow and your isolation valves to do repair work. In my opinion, coming from the plumbing industry, you can never have enough ball valves and isolation valves in a plumbing system to isolate areas to work on. Oh, and the other thing too, okay. Yeah, the other thing too is check valves on each individual dwelling unit, but also important to have a check valve on the return line and have a check valve on the cold water feeding the system, on the cold water makeup. Very important. Okay, next slide. So the next chapter is we're going to talk about optimized loop design. And this is, a very important area because one of the main issues that we have is that there's no widely accepted design guidelines for recirculation systems and design guidelines for recirculation loops. The layout of a recirculation loop may be one of the more crucial of all design elements, as it could perhaps contribute the most to energy losses. As I said before, the amount of heat loss in a distribution system is largely a function of the surface area of the pipe. So it's important when deciding where the plumbing runs go to think about what the shortest routes can be taken and what the smallest diameter of piping can be. In all cases, the locations of the water heaters and the fixtures should also be given consideration at the beginning of the building design. So, minimizing the length of piping not only will save water and energy, but it's also going to reduce construction costs as well. Next slide. So here are some of the main things to consider when designing the layout of the recirculation loop. You want to make sure, again, to minimize the distances from the heating source to the recirculation loop and from the loop to the fixtures. So those branch lines that are going into each unit, you want to keep those as short as possible as well. I know that my friend Gary Klein has a rule that to keep all fixtures within about 12 feet of the main recirculation loop, because in 12 feet of half-inch pipe, you only have a couple cups of water. So you can design a system. It's possible to design a system where you're not wasting any more than 2 cups of water anywhere in the building. So the next thing is to use dual loops. One common practice has always had the boiler room on one side of the building, and then one loop that goes all the way to the far end of the building, and then return line coming back. Instead, what we want to try to do is to make the water heater more central to the building, and then split the loop so that you have 2 loops servicing equal portions of the building, equal zones that cover roughly the same number of units. Doing this will allow you to reduce the effective pipe size. So if you had one gigantic loop at 3-inch, you now may be able to reduce the diameter of that piping down to 1.5 inches or so. So the next thing is to keep the mechanical rooms central part of the building and on the middle of the floor, preferably, so that you reduce the drops in the risers, the distances. And then the last thing is to avoid sharp 90-degree turns. So this is something that we see all the time, is our hard 90 pipe turns. And what that does is it increases the friction losses and actually increases heat losses. Essentially, for every 90-degree elbow, it's the equivalent of adding 3 feet of pipe. So instead of using hard 90s, you want to use sweeping or wide radius elbows. Next slide. Okay, so in this example, we see this is just a very basic illustration of a 3-story apartment building with an optimized circulation loop. I actually pulled this graphic directly from the 2016 Title 24 Compliance Manual. So you see that the water heaters are on the rooftop. It may or may not have solar, but they're on the rooftop central to the building, and then the hot water supply drops to the middle of the building, and then it splits, and then you have 2 return pipes coming back, and then demand controlled. Next slide. And so for some buildings, they're going to have irregular shapes and dimensions, right? So the considerations to where the loops are going to go will, largely depend on geometry. But this gives you an idea that in general, each loop should service the same number of units to minimize pipe size. Now, for very large buildings and buildings that have more than 2 sections, you should think about considering using a completely separate central water heating system for those sections. So in some cases, it doesn't make sense to have one water heating system for an entire building. Next slide. So the last chapter I want to touch upon is system balancing. And system balancing is a little different than balancing in say a hydronic system. So because domestic hot water, you have dynamic flows and temperatures, you don't necessarily want to use the same type of valves that are used for hydronic space heating. If you go to the next slide. So what is an unbalanced circulation system? well, when you have a number of splits in your recirculation loop, and then they come back to make one hot water return line, if you don't have a valve to sort of balance out each of those circuits, you're going to get uneven temperatures and uneven flow rates. And so in this example, you can see that the shortest loop or the shortest circuit is going to have the highest temperature and the highest flow rate, whereas you go down to maybe the other end of the building, it's going to have a lower temperature and lower flow rate. So by placing balancing valves at the end of those circuits, you're going to help to sort of equalize that and get more efficiency out of the system. It'll also make pump controls a lot more viable. What we've seen in buildings that were built without any type of balancing valves, circulation pump controls are next to impossible because you have to have an oversized pump just running 24 hours a day just to get a sufficiently hot water temperature at the far end of the building. There's a number of products that are on the market now that are specifically designed for domestic hot water. They're basically self-actuated, thermo-actuated self-balancing valves. So you put one at the end of each circuit, and when it starts to hit a certain temperature threshold, it'll close off, and then the flow rates will, steadily increase at the other circuits. So that's the idea behind circulation balancing. Next slide. That concludes my presentation on efficient hot water distribution. I just want to leave you with a final quote from Winston Churchill: "We shape our buildings, thereafter they shape us." And I take this to mean that, we spend most of our lives living and working in these buildings, so we might as well do it right, right? Anyway, thank you very much. I appreciate your time. And with that, I will take any questions from the audience.
Thanks, Gabe. Really good content and information. I have a number of audience questions, but sort of a high-level one. I think our experience with the Zero Energy Ready Homes program, both for single-family projects and multifamily, is that anything dealing with hot water distribution and efficiency tends to be a learning curve issue for our project partners and their trade contractor partners. Would you have guidance, tips on how to bring along a project team that for which all this is new? They haven't considered hot water distribution through the lens of energy efficiency and water conservation before. Any guidance on bringing a project team along that learning curve?
I would say, and that's been our challenge, is that there really hasn't been any sort of standard guideline for how to design efficient distribution. Certainly we've been coming a long way in making water heating more efficient. What I would encourage everyone to do is just to look at the latest versions of 2015 IECC, California Title 24. There's some really good ideas about different configurations and different design elements. I touched on a lot of that today, but there's still some other things too worth considering. And it has to come from the design aspect. If you allow plumbing contractors to kind of do things the way that they've always been done, you're just going to get more of the same. So I would encourage you, if you are a plumbing engineer, to focus to see on some of these new criteria that are established. I know that EPA's WaterSense, I think they just came out with some helpful criteria, as well as LEED for Multifamily has a section, I think it's section 7.1 on efficient hot water distribution. So it is getting steadily better, but there's still some work to go.
Great, good response. And even recorded webinars like this one and similar efforts can serve as training resources and learning resources for stakeholders in the industry that are trying to get more up to speed. We had a question about energy analysis of on-demand systems versus more conventional systems, and it came a little bit before you covered those topics, but I guess taking a step back, is there a fairly good body of research that demonstrates the energy performance, maybe benchmarks it of on-demand research versus continuous research?
There actually is, yeah. So there's been studies from a number of different utilities and as well as energy engineers. So Southern California Gas Company, Gas Technology Institute did a really good study. In fact, they have a published white paper on demand controls for multifamily buildings. So I'd encourage you to download that. I think you can download it off of our website actually, but that's got some great information. The State of California, the California Public Utilities Commission has a white paper, or I should say they call it a work paper, and the work paper basically has a description of the measure, but also a synopsis of some of the foundational research. So I'd encourage you to, that's all public information, so I'd encourage you to look up the demand controls work paper. We've been doing a lot of research with some partners out in New York with the Levy Partnership, which I believe was under contract by Department of Energy, and we've done research with DTE in Michigan, out in Minnesota. We've got some research projects, Nicor Gas. So yeah, the body of research is fairly robust. And I think just doing a cursory Google search, you should be able to find that information. But if not, you can certainly reach out to me, and I can provide that for you.
I would just add to that. You're right. The DOE Building America Research Program has funded at least a couple of fairly detailed research projects on this exact topic, trying to monitor and analyze the energy savings and the energy differences between on-demand research and other forms of hot water distribution in multifamily. And they would be available through a site. It's not listed here, but for the audience, it's called the Building America Solution Center. Just look up that search term. And that opens up the entire sort of library of DOE's Building America R&D over the last 15 plus years. But they've packaged it in a really navigable online database that you can search through different structures. One of the ways you can search it is just using the checklist from Zero Energy Ready Homes. So you would drill down, open that checklist, click on the provision that's about efficient hot water distribution, and then it takes you to different resources on that topic. So you'd be able to find some studies of that type through the Building America Research Center as well, or Building America Solution Center as well. Let's see. Pipe insulation. What are your views on truly making it continuous, continuing to insulate the pipes even when you have interruptions, such as straps and framing members? One of the participants today states that they routinely try to get a continuous layer of pipe insulation even at those interruptions.
Yeah. There can be some awkward interruptions in plumbing where you can't necessarily get any insulation on there. My view is anywhere that it's practical to add insulation, do it. It's not going to be possible 100% of the time. I'm guessing, but I think if you can get 90% of the loop insulated, I think that you're going to get 90% efficiency. So yeah, it might not be feasible or practical to do 100% of the loop, but really anything is better than nothing.
Okay, quick administrative question. Will the slides be available? Yes, we're planning on posting them to the DOE Zero Ready website, which is listed here. It would be under the resources page. You'll see a big block on the home page. There's 4 of them actually. One of them is resources. So you click there. They'll be posted within a few days. So it would be the slides as well as the recorded webinar. And in that same portion of the website, you can review and take a look at many other training webinars which we've conducted in the past. Let's see, I have time for a couple more. We had a question, Gabe, on sort of the decision-making factors and why a particular multifamily project might go the way of an individual water heating system contained within the unit versus a central system with a larger hot water plant distributing out to all the different units.
You know, I guess I would have to put myself in the shoes of a builder. I really can't say for certain. You know, my guess is number one is the upfront costs, I think, are a lot less with central hot water. But number two, I think the other thing to think about is, you know, when a central hot water system, when it goes down, you know, everybody in that building is going to be without hot water. Whereas, you know, with individual water heaters, you know, you're not going to have those types of issues. So that's something to consider. But then, you know, also submetering, I think, is a consideration. You know, with individual water heaters, I think most of the time those tenants, they pay for their hot water, whereas in central systems, that's generally an expense that is, if it's not billed back to the tenants directly, it's a cost incurred by the building owner. So I think that's the best answer I can come up with. I really, it's interesting to see too, because certain areas of the country I see a much higher portion of central versus individual, but then I go to another geographic area and I see the reverse of that. So I'm not 100% sure either way.
Yeah, it sounds like it varies by market and by the individual project objectives. We had one question about the threshold for zero energy ready capping multifamily eligibility at 5 stories, and what's the thinking on that? And I believe the thinking is that we need to establish a boundary at some size and height of building. 5 stories has some precedence as a sort of a boundary between multifamily buildings that are low to mid-rise and larger ones. I know the EPA WaterSense program has kind of thought through this question, and Energy Star Homes has thought through this question quite a bit as well, and arrived at that 4 or 5 story band of the market as being close enough to single family in many of the mechanical systems such that they can include those as eligible building types and set the limit at that 5 story level where it currently is. Any comments or observations on that 5 story and how things may differ in buildings beyond that size, Gabe, or any thoughts on that?
Not really. I think you nailed it. I can tell you, seeing, you know, some of the high-rise buildings out in New York City, they are inherently different in terms of how the plumbing is laid out. So I think it is good to sort of just, you know, bite off a certain segment and, you know, get those right before we start moving into, you know, distribution systems that I think are a little more complex and sophisticated.
Very good. Thank you, everybody, so much for your time today and joining us for this webinar. I'll show our contact information here on the slide just for another second, and we'll bounce back up one slide to Gabe's contact info with the Enovative Group, and we'll close it out now. Again, thank you very much for participating. These slides in the recorded webinar will be available on the DOE ZERH Energy Ready Home website within a few days. Thanks so much for joining us, everybody. Bye-bye.